Good morning to all of you. In previous sessions, we had discussed properties of Z transform. Started with the linearity property, then we have seen time shifted property, then we have seen scaling in the Z domain, we have seen time reversal property, and in previous session we had discussed the differentiation in the Z domain property. In today's session, we will be discussing another property of Z transform, that is convolution of two sequences. We will try to identify the convolution by using Z transform, by using the convolution of two sequences property. So in convolution of two sequences property, if we have two discrete time signals, that is x1 of n and x2 of n. Okay, so we want to identify the convolution of these two signals, that is x1 of n and x2 of n. If x1 of n has the Z transform capital X1 of Z and x2 of n has the Z transform x2 of Z, then the convolution of x1 of Z and x2 of Z, if I am representing that convolution as x of n, and the convolution of x1 of Z and x2 of Z as x1 of n convolved with, we know that this star operator is the convolution operator. So x1 of n is convolved with x2 of n in Z domain. See, we have been provided with two discrete time signal, that is x1 of n and x2 of n. So x1 of n has the Z transform x1 of Z and x2 of n has the Z transform x2 of Z. Then the convolution of these two signals, that is x1 of n and x2 of n, is represented as x of n. So we are convolving x1 of n with x2 of n. So in Z domain, this convolution is simply the multiplication of their respective Z transform. That means x1 of Z multiplied with x2 of Z. Okay. So here we are multiplying x1 of Z and x2 of Z in the Z domain. Okay, so their multiplication result can be represented as capital X of Z. Okay, so convolution in time domain, the convolution of two discrete time signals in time domain is simply the multiplication of their respective Z transform in the Z domain. Okay, so we know that the convolution, for identifying convolution, we have seen different methods. Okay, we have seen graphical method, we have seen tabular method, we have seen matrix method, we have seen mathematical method. Okay, so for identifying the convolution of two given sequences, any one of those methods can be utilized, right? But even the convolution can be only used to identify the response of the two sequences, right? Or the response of the given discrete time system, if it is an FIR system, that is finite impulse response system. We cannot use convolution to identify the response of infinite impulse response system. There we can use the difference equation. We have seen all these things, right? But here we are utilizing the Z transform to identify the convolution of the two sequences. That means we are utilizing the Z transform to identify the response of given system, okay, by using its input response and the impulse response. Here we can consider that x1 of n is the input signal and x2 of n is the impulse response of the given discrete time system. So that means we can utilize the Z transform to identify the uh, response of given discrete time system. Okay, so again Z transform is one of the tool to analyze given LTI system. Okay, so here again the ROC of this resulting result, that is x of z, is simply the intersection of ROC uh, is that is ROC of capital X of Z is at least the inter intersection of ROCs of x1 of z and x2 of z. Okay. So here we'll try to prove this property, right? So in proof, okay, I can write here initially the signal x of n. So x of n is the convolution of x1 of n and x2 of n. Okay. So as per convolution property or formula, we can write here the convolution of x1 of n and x2 of n can be represented at summation k is equals to minus infinity to infinity x1 of k into x2 of n minus k. We know that the convolution of x of n with h of n, okay, is represented summation. We represented this convolution as y of n. Okay. We have seen this, right? So this convolution y of n, which is the convolution of x of n with h of n, is represented as summation k is equals to minus infinity to infinity x of k into h of n minus k. Okay. So we have seen this. So here we are representing, or we are identifying the convolution of x1 of n and x2 of n. So this can be represented k is equals to minus infinity to infinity x1 of k into x2 of n minus k. Okay. So this is your what, x of n. The Z transform, okay, the Z transform of x of n is given as what, or represented as capital X of z, and which is nothing but summation n is equals to minus infinity to infinity x of n into z to the power minus n. That is the formula for Z transform of x of n. Okay, but here in this case x of n is nothing but the convolution of x1 of n and x2 of n. Okay, so we can replace that x of n with this, that is summation k minus infinity to infinity x1 of k into x2 of n minus k. Okay, so I can write here summation n is equals to minus infinity to infinity. In place of x of n, I can substitute k is equals to minus infinity to infinity. To that k minus infinity to infinity x1 of k into x2 of x1 of k into x2 of n minus k, right, into z to the power minus n, right. So I replace this x of n with the convolution of x1 of n and x2 of n, right. So here again I can take this k minus infinity to infinity x1 of k outside this summation and minus infinity to infinity. Okay, so I will make some adjustment here to reduce or simplify these terms. Okay, so I will keep this k minus infinity to infinity x1 of k outside this summation n is equals to minus infinity to infinity, right. So remaining terms are x2 of n minus k into z to the power minus n, right. So here to this summation n minus infinity to infinity x2 of n minus k into z to the power minus n, you can apply the time shifting property. Okay, here we can apply the time shifting property. So again, as per the time shifting property, what we are saying, if x of n has the z transform x of z, then what, like small x of n minus k has the z transform z to the power minus k into x of z, right? So that is the time shifting property, x of n having z transform x of z, then x of n minus k has the z transform z to the power minus k x of z, right? So here this x2 of n has the z transform x2 of z, then x2 of n minus k has the z transform z to the power minus k x2 of z, right? So this complete bracket can be replaced with z to the power minus k x2 of z. So here we can write summation k is equals to minus infinity to infinity. This x1 of k will be as it is, and in place of this complete bracket you can replace it with z to the power minus k capital X of capital x2 of z. Okay, because x2 of n has the z transform x2 of z. Okay, so x2 of n minus k, again this is the formula for z transform. Okay, this bracket is nothing but the formula for z transform, and in this bracket we are identifying the z transform of x2 of n minus k. So here we can apply the time shifting property because x2 of n has the z transform x2 of z, right? So x2 of n has the z transform x2 of z, so therefore x2 of n minus k has the z transform z to the power minus k x2 of z. Okay, so again in this case this summation k minus infinity to infinity x1 of k into z to the power minus k, it is again nothing but the formula for z transform. Only difference is that here the summation of variable is k instead of n, but it is the formula for z transform. So in place of this formula again, that is, or in place of this bracket, that is summation k minus infinity to infinity x1 of k z to the power minus k, we can replace it with capital X1 of z, because here we are identifying the z transform of x1 of n. Okay, small x1 of n. Okay, so in place of n we are simply using variable k. Okay, but it is the formula for z transform. So here you can simply write it down as this bracket can be replaced with capital X1 of z, right? So this capital X1 of z multiplied with this capital X2 of z will be this. Okay, so therefore we can say that the convolution. Okay, so this x1 of z multiplied by x2 of z is nothing but here capital x of z, right? So therefore here we can say that the convolution of x1 of n, that is x1 of n convert with x2 of n in z domain, is simply the multiplication of their respective z transform, that is x1 of z multiplied with x2 of z, and this multiplication result were indicated as capital X of z, convolution were indicated as x of n. So this is nothing but the convolution of two sequences. Okay, so again ROC is simply the at least intersection of these ROCs of x1 of z and ROC of x2 of z, right? So this is convolution of two sequences property of z transform, right? So let's try to solve this example. So here we are computing the convolution x of n of signals x1 of n and x2 of n by using z transform. Okay, so again this convolution, the convolution of x1 of n and x2 of n is simply represented as x of n, and it is x1 of n convolved with the star operator is nothing but the convolution operand convolved with x2 of n, and as per convolution of two sequences per t of Z transform, the convolution x of n is x of n in Z domain is simply capital X of Z is equals to the Z transform of x1 of n, that is x1 of Z, multiplied with Z transform of x2 of n, that is x2 of Z. Okay, so that means we have to initially identify the Z transform of x1 of n, that will be represented as x1 of Z, and then we'll identify the Z transform of x2 of n, which will be represented as x2 of Z. Then we'll multiply their respective Z transform. Okay, so let's initially identify Z transform of x1 of n. Okay, so it will be represented as x1 of Z, and the formula will be n is equals to minus infinity to infinity x1 of n into z to the power minus n. Okay, here origin is not given, so you can consider this first sample as the origin sample, right? So this sequence is starting from 0, right? N is equals to 0, next value will be 1, next will be 2, so it is starting at n is equals to 0, ending at n is equals to 2, right? So here you can modify these summation limits for x1 of z as summation n is equals to 0 to 2 x1 of n into z to the power minus n. Okay, so again, if I'm substituting these values, so equal x1 of 0 z to the power 0 plus x1 of 1 z to the power minus 1, right, plus x1 of 2 into z to the power minus 2. If I'm substituting the values of x1 of 0, x1 of 1 and x1 of 2, so these values are 1 minus 2 1, so it will be 1, z to the power 0 is 1, x1 of 1 is minus 2, so it will be minus 2 z inverse, right, and x2 of 2 x1 of 2 is 1, so it will be plus 1 z to the power minus 2. Okay, so this is the required Z transform of x1 of n, right? Similarly, identify the Z transform of x2 of n. Okay, so what will be the Z transform of x2 of n? Again, it will be represented as x2 of z. Formula will be summation n is equals to minus infinity to infinity x2 of n into z to the power minus n. Okay, so again, in case of x2 of n, so the value of x2 of n is 1 for 0 to 5. Okay, for n greater than or equals to 0 and for n less than or equals to 5, the x2 of n has the value 1, and for other values it is 0, so it will only exist for the limit 0 to 5. So here again summation can be taken from n is equals to 0 to 5 x2 of n into z to the power minus n, and again here you can put these values, so x2 of 0 z to the power 0 plus x2 of 1 z inverse plus x2 of 2 z to the power minus 2 plus x2 of 3 z to the power minus 3 plus x2 of 4 z to the power minus 4 plus x2 of 5 z to the power minus 5. Again, for these different values 0 to 5, the value of x2 of n is 1. Okay, so there you can substitute one value. So here I can substitute 1. So x2 of 0 is 1. 1 multiplied by z to the power 0. Z to the power 0 will be 1 again. So it will be 1 plus 1 multiplied by z inverse. So it will be z inverse. 1 multiplied by z to the power minus 2. Z to the power minus 2. Z to the power minus 3. Z to the power minus 4. Z to the power minus 5. Okay. So this will be your x2 of z. Okay. So now we have got x1 of z and x2 of z. Now let's multiply these two sequences. So as per the convolution of two sequences property, we have to multiply this x1 of z with x2 of z. Okay. So to get the x of z. Okay. So x1 of z is 1 minus 2z inverse, 1 minus 2z inverse plus z to the power minus 2, and x2 of z. So what we are doing here, we are simply multiplying x1 of z with x2 of z. Okay. And x2 of z is 1 plus z inverse plus z to the power minus 2 plus z to the power minus 3 plus z to the power minus 4 plus z to the power minus 5. Okay. So this is nothing but your x1 of z multiplied by x2 of z, right? So let's multiply this and simplify this equation. So initially I will multiply 1 with this complete bracket, so I will get 1 plus z inverse plus z to the power minus 2 plus z to the power minus 3 plus z to the power minus 4 plus z to the power minus 5, right? Then minus 2z inverse, I will multiply with minus 2z inverse, right? Minus 2z to the power, this z inverse multiplied by z inverse will be z to the power minus 2, right? Again minus, so I have to multiply it with z inverse with each term, that is minus 2z inverse, so these powers will be incrementing by 1, so it will be minus 2z to the power minus 3 minus 2z to the power minus 4, right? Minus 2z to the power minus 5 minus 2z to the power minus 6. Okay, that is minus 2z inverse multiplied by z to the power minus 5 will be z to the power minus 6, right? 2z to the power minus 6. Next I will multiply it with z to the power minus 2, so it will be plus z to the power minus 2, right? Plus z to the power minus 3 plus z to the power minus 4 plus z to the power minus 5 plus z to the power minus 6 plus z to the power minus 7. Okay, that is the multiplication. Now let's add and subtract, right? So this is z inverse minus 2z inverse. Okay, so first I'll write 1, so z inverse minus 2z inverse will be minus z inverse. Okay, next I will identify z to the power minus 2 term. So here z to the power minus 2 is there. Again minus 2z to the power minus 2. So minus z to the power minus 2 will be there. Correct. And then it will get cancelled with this one. So it is the 2z to the power minus 2. It will get cancelled with this one. That is 2z to the power minus 2. Right. Similarly, z to the power minus 3 is there, right? So z to the power minus 3, here also z to the power minus 3, so it is 2z to the power minus 3 minus 2z to the power minus 3. Okay, so it will be 0, right? Similarly, z to the power minus 4, z to the power minus 2, z to the power minus 4, so it will be minus z to the power 4 plus z to the power 4 will be again 0, so this will be 0 again. So again z to the power minus 5, right? Minus 2z to the power minus 5 will be minus z to the power minus 5, and it will be plus z to the power minus 5 will be 0. Okay. Next terms are, we already taken this term, right? We subtracted z inverse with minus 2z inverse, it is minus z inverse, right? Then remaining terms are minus 2z to the power minus 6 plus z to the power minus 6. So it will be minus z to the power minus 6 and plus z to the power minus 7. So this is the final multiplication result of x1 of z multiplied with x2 of z. Okay, but we are interested in identifying the convolution. As in example, it has been asked to compute the convolution x of n. So that means from x of z, from x of z, identify x of n by taking the or by finding the inverse z transform of x of z. That means we have to take the inverse z transform of this capital X of z. Okay, but again there are methods for identifying inverse z transform. Okay, so that is Cauchy-Residue method, then there is long division method, and there is partial fraction expansion method, right? So we are not using those methods, but again here we can directly identify the inverse z transform from this x of z. So how we can identify it? So we know that the z transform of this x1 of n is x1 of z, right? We can directly write this z transform as what? 1 plus here minus n minus 2z inverse plus what? Z to the power minus 2. So what will be its inverse z transform? So simply the coefficients. Okay, so at n is equals to 0, the coefficient is 1, right? At n is equals to 1, it is minus 2, and at n is equals to 2, it is 1. So its inverse z transform will be simply represented as x1 of n, so it is 1 minus 2 and 1. Okay, so from x1 of z we identified here x1 of n, correct, by simply writing their coefficient at different values of n. Okay, here n is equals to 0, here n is equals to 1, here n is equals to 2, correct. Similarly, here also you can identify the coefficients to write down the sequence x of n, that is the inverse z transform of x1, sorry, x of z, right? So at n is equals to 0, the coefficient is 1 here, right? At n is equals to 1, the coefficient is minus 1, right? At n is equals to 2, there is no value present, that means coefficient will be 0, right? At n is equals to 3, again coefficient will be 0. At n is equals to 4, at n is equals to 5, okay, all will be 0. Directly coefficient present at n is equals to 6, so it is minus 1, so the value will be minus 1. And at n is equals to 7, it is again 1. Okay, so that will be the final x of n. Okay, so here origin will be at this 1. Okay, so here we identified the convolution. By using the convolution of two sequences property of z transform. Okay, so it is simple method compared to what we have seen, the graphical method or maybe tabular method or mathematical method, right? So we can efficiently compute the convolution of two sequences by using z transform. So what we have to do to compute the convolution of two sequences by using z transform? So initially we have to identify the respective z transform of each signal, that is we are identifying z transform of a signal as x1 of z, second signal as x2 of z, and then we have multiplied their respective z transform to get the final product, okay, result. So their multiplication is represented as x of z, that is x1 of z multiplied with x1 of z multiplied with x2 of z. Then after multiplication we are identifying the inverse z transform. So it is somewhat simpler method compared to the actual computation of the convolution. Okay, So to summarize, the convolution property is one of the most powerful properties of Z transform because it converts the convolution of two signals from time domain to multiplication of their respective Z transform. Okay, so it converts time domain into multiplication of their respective Z transform into Z domain. So computation of convolution of two signals using the Z transform requires these three steps. Okay, so in first step what we have done, so we have computed, so compute Z transform of given two signal. Okay, so compute Z transform of the signals to be convolved. Okay, so initially we will be identifying the Z transform of the given signal. Okay, so in this case we identified x1 of z, that is nothing but the Z transform of x1 of n. Okay, and for second signal x2 of n, its Z transform is x2 of z. Okay, so here initially signal was in time domain. Okay, so we're transferred to Z domain. Okay, so we shifted it from time domain to Z domain. In second step, we are simply multiplying the two Z transforms, that is x1 of z and x2 of z. So multiply the obtained two Z transforms. Okay. So this multiplication is x1 of z multiplied with x2 of z. So this is simply represented x of z, and this is in Z domain. Okay. And third, we are identifying the inverse Z transform, right? So find the inverse Z transform of multiplication result, that is x of z. So that inverse Z transform can be represented by x of n. Okay, we are obtaining x of n from x of z by taking its inverse Z transform. Okay. So here what we are doing, the Z domain signal is converted to time domain. So this Z domain signal will be converted to time domain. So the computation of convolution by using Z transform involve these three steps. Okay, and this procedure is computationally easier than the direct evaluation of the convolution summation by using whatever methods we have seen. Okay, so basically if we want to uh, perform the convolution operation by using computational algorithm or by using or by writing some program, so there we have to what we have to implement it using the mathematical formula of convolution. Okay, so it requires more number of operation, as we have seen in the computation of two sequences by using convolution formula. It involves four steps. Okay, in first step we are doing folding operation, in second step we are doing shifting. Okay, then we are performing addition operation, sorry, multiplication operation, and then finally performing the addition operation, but it will be performed for each value of n. Okay, so it comprises more number of computations, identifying the convolution by using the mathematical formula. Okay, so it involves more number of computational operations. So if we want to identify the convolution by using Z transform, so it is somewhat easier compared to the uh, actual evaluation of the convolution summation. So by using Z transform, we can reduce the number of computational operation involved in the computation of convolution of two sequences. Okay, so in today's session we will discuss this convolution of two sequences property of Z transform. Okay, we also seen its proof, and we've seen one example where we had identified the convolution by using the Z transform. Okay, so in next session we'll be discussing correlation of two sequences property of Z transform. So thank you for joining this session.